Lensmaker's formula. It is the relation. It is the relation that is the used by the lens makers to design lenses. So this relation actually gives you the relation between the focal length, the radius of curvature of the lens, and its relative refractive index. Actually, if you see any convex lens or a concave lens, you will see it has two surfaces, that is x, y, z and x, y dash, z. So definitely their radii of curvatures can be same or it may be different. So as a result, what happened, the lens behaves accordingly. If the radii of curvature is different or same, it behaves accordingly. The capability of the lens also depends on what kind of refractive index it is in its surrounding. So this is N2, this is N1, N2 being the absolute refractive index of the material of the lens. Okay, so let us derive this relation. In order to derive this, first let us consider an object. If you have seen my last video or last numerical regarding that boy who is watching a toy car through a glass sphere, it is exactly based on that. That is the foundation for this derivation. So let's see how to do it. Imagine this is a point object on the principal axis of the double convex lens. This double convex lens radius of curvature is different. This radius, this face XYZ radii curvature is R1. Let's say it is at a distance of, so let's say this is R1, and for x, y prime, z, it is this side. This is second surface. So this is R2. So a point object is on the principal axis of the in front of the convex lens. A ray originates from this lens. A ray originates from this lens and is incident on this surface x, y, z, where it undergoes refraction. And after refraction, inside the medium the ray goes like this, and then it produces a virtual image somewhere here. This is I dash. So this is the virtual image that the first surface XYZ produces. Now for the second surface, this lens acts as an object. This image, intermediate image I prime, act as an object, and then again refraction takes place at the interface x, y prime, z, and the final image is formed somewhere here. The final image is formed somewhere here, say. So this is the ray, this is the path of the ray, this is the final image I. You can easily draw the normals also. If you see, this is the, from here, for this surface where the refraction is taking place, this must be the, this must be the normal, right? And for this surface, this must be the normal. Okay, so let us establish the relation now. Let us define the different distances. First of all, this distance, all the distances will be measured from the center of the lens. So as the lens is very thin, so we can do that. So from the O, the object O is a distance of u from here. The intermediate image is at a distance of V1 from I, and the image I, the final image is at a distance of V from there. Okay. Then there are radius of curvatures also. This is R1. Okay, I have already mentioned it. Let us not make it, let us not clutter it much. So let us derive it. So at the interface, at the surface XYZ, the refraction is taking place. So which relation to use now? Minus 1 by u plus the relation is the rays traveling from medium 1 to medium 2. So I should be writing here going from 1 to 2 divided by v equal to 1 to minus 1. So wait a minute, the image is formed at v dash v1 divided by r1. R1 means the radius of curvature of the first length. Is it positive? Yeah, it's positive, correct. And then let us go to the next one. So this relation, if I simplify it, I can write like this: minus, this would be 1 by u plus n2 by n1 into v1 equal to n2 by n1 minus 1 by r1, right? So finally we can write this as minus n1 by u plus n2 by v equal to v1 n2 minus n1 by r1. On simplification we can write this. So this is our equation 1. Now refraction at the second surface. Refraction at the second surface, the virtual image I dash act as object for the second interface x y dash z. So now the ray is traveling from denser to rarer, that is n2 to n1. So our relation will be now minus 1 by u plus going from 2 to 1 by v equal to 2 1 minus 1 by r. So this is, wait a minute, in this case u will be what? In this case u will be the v1, because v1 is the object for the second surface. So this one would be minus 1 by v1 plus 2 n1 by v equal to 2 n1 minus 1 by r. Wait a minute, is this going to be minus or plus? Okay, it's fine, it's thing only, no need, because you can see this, check the sign convention. Sign convention is always, it is coming same only, no need to worry. So now we can simplify and write this 1 by v1 plus this one would be n1 by n2 into v equal to again n1 by n2 minus 1 by, so this one would be r2, sorry, this one would be r, because it is second curvature, right, second radius of curvature. So in this case radius of curvature is will be r2, correct. So next case, you remember why I am writing n1 2, because we know that from 2 to 1 it would be n1 by n2, and from when you go from 1 to 2 it would be n2 by n1. Always in the numerator always will be the second medium first. So the next next page. So this relation now becomes minus n2 by u v1 plus n1 by v equal to n1 minus n2 by r2. This is equation 2. Now, if I add 1 and 2, what do I get? So, first equation is minus n1 by u plus n2 by v1, then this one again minus n2 by v1 plus n1 by v equal to n2 minus n1 by r1 plus n1 minus n2 by r2. Clearly we can cancel this two. So, what is left now? Minus n1 by u plus n1 by v equal to n2 minus n1 by r1 minus n2 minus n1 by r1. Let us take minus common and write this one like that way. So, I can take n2 minus n1 common out. So, this becomes 1 by r1 minus 1 by r2, right. So, next I will take, so n1 common out, 1 by v minus 1 by u equal to n2 minus n1 1 by r1 minus 1 by r2. So, 1 by v minus 1 by u will be n1 by n2, sorry, n1, this is 1 by r1, that gives me 1 by v minus 1 by u equal to n2 by n1 minus 1 by 1 by r1 minus 1 by r2. Or now we can write this. If you remember the length equation, from length equation we know that for thin lengths 1 by f is equal to 1 by v minus 1 by u. So, we can easily write this equal to n to 1, means it is 1 to 2 minus 1 1 by r1 minus 1 by r2. So, this is the length makers equation. Most of the time we are going to write this expression 1 by f is equal to 1 n2 minus 1 1 by r1 minus 1 by r2. So, this is the length makers equation. Now, one particular case. So, this is our relation 1 by f is equal to 1 n2 minus 1 1 by r1 minus 1 by r2. So, if you note, let us say that this is a double convex lens. So, this is the lens whose both of the radius of curvature is same. So, this is r1 and this is r2. So, r1 equal to r2 equals to r. So, if this happens, this is case, one particular case, then what you see what happened now, 1 by f is equal to 1 into minus 1 1 by r minus r, because if this is the length, this side is DOL. So, here r1 is positive, however, r2 would be negative. So, then this relation becomes 1 n2 minus 1 1 by r plus 1 by r, okay, 1 by f is equal to 1 n2 minus 1, this gives me 2 by r. Now, let us say the lens is made of glass. If the lens is made of glass of N2 equal to 3 by 2 and is present in air, that is N1 equals to 1, then you see 1 by F equal to N2 by N1 minus 1, 2 by R. So N2 is 3 by 2, so 3 by 2 minus 1 because N1 being 1, and this is 2 by R. So 3 minus 2 is 1 by 2 into R by 2, 2 by R, 2 by R, 2 get cancel, 1 by F is equals to 1 by R. So this implies F is equals to R. So in case of double convex lens or double concave lens, it would be what? For in case of double convex lens, it would be plus F and it would be minus F in case of concave. But in case of double concave or double convex, where both the R1 and R2 are same and one of them is and they made of glass placed in here, the focal length is equal to radius of curvature. So if I give you a question that you will see in future numericals that I will write the radius of curvature of lens is 20 centimeter. So that time you will understand it is the focal length is also the 20 centimeter. So this is a very important proof from the relation. Okay, we will be doing more numerical on this one as we have introduced two lens makers formula. This is another advanced topic in refraction, actually a practical application of refraction. Okay, see you in next topic.